In this particular video, we are going to look forward for what is called a covector. Very good evening and a warm welcome to all the people who are watching this video. If you have watched my previous videos, we have spoken much about covariant and contravariant vectors, and this particular video we would be concentrating on the concept which is called covector. Before we go ahead and start with covector, I would like to quickly show a basic revision on the topics that we have covered earlier. Well, yes, here are the topics. So I have just listed it down. You can have a watch, you can just have a quick look onto it. So we have seen what is called a covariance. Right, we have seen two parts of covariance. One is the statistical approach of covariance, one is the mathematical approach of covariance. We have also seen what is positive and negative covariance, how the positive covariance goes forward with variables when two variables are moving in the same direction, and what is a negative covariance. We have also seen this formula, point 3, covariance of x and y equals to sigma of xi minus x bar, yj minus y bar, whole divided by n minus 1. If you have watched my earlier video, we have shown a case study in which we have used this formula. 4 is that we have also seen that what is covariance in terms of calculation of population. So it is little bit different, sigma xy, summation of xi minus mu x minus yi minus mu y divided by n. This is a covariance in which we calculated the case study. This is basically the population covariance. We have also seen a case study, and if you remember that there was a person who was willing to invest in two companies, and before going that he wants to find out whether there is any correlation between those two. So we have seen earlier in this video that correlation and covariance are things which are quite related to each other. Only in the case of correlation the values goes between plus positive 1 to negative 1. In case of covariance of mathematical calculation, it doesn't show. We have also seen in the 6th point that 1 means positive correlation, 0 means no correlation, and minus 1 is negative correlation. If you have seen the earlier video, then you have seen that I have shown 4 or 5 graphs in which these correlations are related to each other. So this is a nice summary on what we have learned earlier. And now what we will do is that we will go ahead in learning what is called a covector. Now, before we go ahead and calculate what is called a covector, what I would like to show you is that what is a covariance matrix. And before even going ahead to show what is a covariant matrix, we have seen sufficiently what is a covariant and a contravariant components, vectors, etc. But all we have seen is mathematically. So here is an attempt of mine in which I am trying to show a kind of a visual representation of what is a contravariant and a covariant component. Now, I would like to show you this graph particularly. Okay, so you see this is the y-axis and this is the x-axis. This is the vector which is projected in this direction. You can call this v. I have not mentioned it. Now say for example, this is a contravariant component which I am trying to show. So what is going to happen if I put my pen over here and if I slide this pen towards this direction, so this one is moving in this direction, what is going to happen is that the perpendicular which is dropped from the vector is also going to move in this direction, So what is going to happen is that if you see this is moving in this direction, whereas this is moving in this direction, these two are parallel to each other. So I have written this to be a parallel projection. But do you notice a very important factor in this in this figure? If I take the y-axis as 0 as origin, and if this axis is moving in this way, 0, 1, 2, 3 and so on, if you see the parallel projection is also moving in this way, but it is moving in the opposite direction. So once these y-axis moves from point 0, which is the origin, to 1, 2 and 3, this values moves from point 3 to 1 and towards 0. So that is why we call it as contra. This component is moving towards this direction, whereas this component is moving exactly in the opposite direction. As it moves from 0 to 3, it moves from 3 to 0. So it is opposite movement. So that is why it is called a contravariant component. So this is moving this way, this is moving this way. This is just a kind of my attempt to show what is the visual representation of a contravariant component, which is a parallel projection. If you look in this figure, you will see this is a perpendicular projection, which is the contravariant component. So if you see this same y-axis which is moving in this way, then this part will move in this way, right? It is moving with a perpendicular projection. That means each of these angles, if you see this angle, if you see this angle, if you see this, all these are 90 degrees. So each of them are perpendicular projection. So just remember one thing, that covariant actually shows a parallel projection, whereas contravariant component shows a perpendicular projection. You can also see from this video how this axis is moving in this way, and it is moving from 0 to 3, whereas this is moving from 3 to 0, which is an opposite, and hence it is called contravariant. Whereas in this part, it is just a perpendicular projection, so it is moving in this, and each of the angles formed are perpendicular, and that is why it is called the perpendicular projection. Okay, so we are good to go. We have shown you a visual representation of co and contravariant vectors, how these are related. And before we start showing you what is a covector, what I'm going to show you is that what is a covariance matrix. I think I have shown this in the earlier video, but that was in a rush, so I will explain to you in a better fashion, and this is how it happens. For example, we have taken a graph, and here there are two variables, x and y. The value of x when it is 1, the value of y it is 1, the value of x when it is 3, y is 0, and the value of x when it is -1, y is -1. So if I go ahead in projecting these values, then what will I get? So if I take the first case, so x equals to 1, y equals to 1, that means it will be moving in this direction. So this is 1, right? Now when x is 3, so we get x equals to 1, y equals to 1. So x is moving here, y is moving here. So we get a kind of a direction like this, right? Now the second case shows that when x equals to 3, y equals to 0. So we have to go by the explain 1, 2, 3. So we move up to here. So this is the line. Now when x equals to -1, y equals to -1, so we get something like this. So this is something that that shows that how we can plot the values of x and y on this graph. Now in order to show what is a covariance matrix, so what we will do is that, okay, so what we will do is that first of all, it is a 2 by 2 matrix. We are considering this to be a 2 by 2 matrix so that we can avoid bigger calculations. So first of all, as we have learned earlier, let us say, for example, we write, say, covariance, okay, of these first two values. So we write x and x, then we write covariance of x and y, right? Then what we do is that we will write the covariance of the second value, that is covariance of y and x, and then we will write the next one, what is the covariance of the next value, that is covariance of y and y. Covariance of y. So what we are going to do is that we are going to put this in matrix form, right? And I can mention this one as x and y in this part, and also in this part I can mention as x and y, right? Now there are a few things which you need to understand before I go ahead in putting the values or deducing the values. The covariance between the values itself, that means the covariance, okay, let me put it in red. Covariance between the values itself, that is the covariance of xx and the covariance of yy, right? So covariance of xx and covariance of y is basically called the variance. So I can call this one as variance, okay, of x, and this one I can call variance of y, right? So covariance between the values itself is the variance. Now you might say that what is the difference between the between the values of covariance of xy and yx? What is the difference between the covariance of xy and yx? Fact is that there is absolutely no difference. I will repeat, the covariance between x and yx, there is no difference. That means that covariance matrix itself is a symmetric matrix. This variance is a symmetric matrix. It is something like, what is the difference between A and B and B and A? There is no difference. So I can write, so this is something which can be written something like this. So if I take values like 1, 2, 3, and if I take 2, 4, and 5, and if I take 3, 5, and 8, okay, and I can use the transpose, which will be something like 1, 2, 3. If I put this in this way, I hope you understand. 2, 4, 5, and 3, 5, and 8. So this becomes the transpose. So I can therefore put up, if this matrix is named as A, transpose of A equals to A, right? That means, so this is what it is called, that covariance itself is a symmetric matrix. Now, so from here, what I can show you is that the covariance of x and y will be equal to the covariance of y and x, just in the way that, say for example, if I put the value of a and b is equal to the values of b and a, right? So just note that this actually obeys the commutative property, okay, but please note that matrix multiplication is non-commutative. As you know by the formula of linear algebra, that matrix multiplication itself is non-commutative, but here, because of x and y and y and x, this follows the commutative rule, right? Now what we are going to do is that we are going to calculate the values, that is that we are going to calculate the variance. Okay, before we do that, so what we can do is that I have just summarized what we learned till now. So you see that covariance of x, what it does is that it, okay, this is not the summary part. This will come later. Anyway, so what we can do is that we can use, so there are a few points which are worth noting from this particular deduction. One is that covariance between the variables itself is the variance. So covariance between xx and covariance of yy itself is the variance. There is no difference between the covariance of xy and yx, just in the way we did that AB and BA actually carries no difference. Covariance matrix itself is a symmetric matrix. That means if we flip this part, it will be exactly the same, which we have shown with an example. Now say for example, we will take those values, okay, and what we are going to do is that we are going to calculate a little bit the values, and we will actually put those values in the covariance matrix in order to see that how actually a covariance matrix looks like. So let us write those values once more over here, and let us see that how we can actually calculate them. So here are my variables, x and y. This is for a visual representation. I will draw a line so that things becomes clear over here. So what are the values which we know? We know this is 1 and 1, 3 and 0, and we have got -1 and -1. So these are the values which we have already got. Now I have to show you what is actually the formula for calculating the covariance. So first of all, we will calculate the covariance between x and y. This is the first. So you can call it the covariance of x and y is basically the estimated values of x, y, okay, minus the estimated value of the first variable, that is x, and product of estimated value of y. Okay, so this is a nice formula through which we are going to do the calculation. So I will just repeat it once more. The covariance of x and y is the estimated value of x and y minus the estimated value of x product multiplied by estimated value of y. Okay, so let us see that how we are going to calculate the estimated values of x and y. So we know here, okay, so what we can do is that we can write equal to the estimated value, and I put a bigger bracket so that it becomes easier. So 1 multiplied by 1 is 1, 3 multiplied by 0 I put it, and minus 1 multiplied by minus 1. Okay, so what do we get? Say for example I get 1 multiplied by 1 equals to 1, 0 is 0, and minus 1 is plus 1. Okay, and then we calculate 1 plus 1, 2, and the total value is 1, 2, 3, so it is 2 by 3. Right, now we haven't calculated the mean, so we are going to calculate the mean also. So how do we calculate the mean of this? Simple. So we calculate this one gets cancelled out. This is 3. So 3 divided by number of times of occurrence is 3. It's 1. So this one and this one becomes 0. Right, because this cancels out. Right. So now we have got this value. So what it is quite simple. So and this part x and y, because the estimated value of y is already 0, so this becomes already 0. This part is already 0. So this is the value 2 by 3. Right. Now let us see that how we can calculate the covariance of x and x. So covariance of two variables x and x. So I will use the same formula. I will just replace this y by x. So I get the estimated value of x and x minus estimated value of x multiplied by estimated value of x. So what we get over here, this one will become estimated value of x squared minus estimated value of x squared, right? Okay, so how do we calculate the estimated value of x? So let us see that. So we have to square those. So 1 square will become 1, 3 square will become 9, and minus 1 whole squared will become positive 1. So we get this value 9 plus 10 plus 1, 11, 11 divided by 3, right? And this one is already 1. We know that this from 1. This x square is 1 because this is calculated. So it would be minus 1. So 11 by 3 minus 1 comes to 8 by 3. Right? So we have calculated the values of x and x, which is 11 by 3. Now comes the remaining part, that is the covariance of y and y. So let us see how we can calculate the covariance of y and y. So we take the same covariance of y and y. It is same, the estimated value of y. I'm again not writing it, so you already know it is y squared minus again estimated value of y squared. Now we already know the estimated value of y is 0, so this will strike off, this will become 0. And what is the estimated value of y? Let us see, we can calculate it further. It would be 1 into 1, 1 squared equals to 1, then 0 squared equals to 0, and minus 1 whole squared will become plus 1. So we take this value as 2 by 3. Right, so we are done with the calculation of values. So what are the values we calculated? We calculated covariance of xx, xy, then the xx and yy. Now it is the time that we can put it together in the matrix. So what is the first value that we calculated? This one is the first value. Okay, let me show you the graph so that it becomes easy. Right, so what we have to put xx, yxy, yx, yy. Fine. So this is what we are going to put. Okay, so here is my page, and we have to put those values. So the first value is 8 by 3, so we put it as 8 by 3. Second value is xx, and then xy, we got it 2 by 3, right? Xx, xy. Yeah, covariance of this is also 2 by 3. Yeah, 2 by 3. Right. So we put it as 2 by 3. Now obviously what is going to happen is that because it is a symmetric matrix, the next part is obviously going to be 2 by 3. We don't have to look for further calculations, and covariance of y and y is 2 by 3. Right, so we can now put the braces around. We can put the braces around. Right, so this is my first calculation in which I have shown the values of covariance matrix, right? So this is how we can calculate the values of covariance matrix. So just remember one thing, that when we are going to calculate the values, we are actually calculating the value of xy with this formula. In case that you are calculating values of both with the same variables s and x, all you need to do is that just substitute this one with x's, so estimated values gets calculated and you can get the total value. So covariance matrix, I think it is quite clear. We have shown that how the covariance matrix between these two, that is xx, yy and further, are basically the variance. Covariance matrix itself is a symmetric matrix, so if you transpose it, we get the same values. Covariance between the two variables x and y, and the covariance between the other two variables y and x, they are the same. There is absolutely no difference between the two. And we have also seen that we can calculate those estimated values, and we can in this part, and we can show you how a real life covariance matrix looks like. Now let us see that if we go into a 3-dimension, how the covariance matrix will look like. Right, so here I have taken 3 variables, like it is a 3-dimension, xx, xy and xz. Now just note that what is happening in this particular 3 by 3 matrix, that covariance, the variance calculation is this. This part, and this part, right? So I can put it as this one, I can put it as this one, and put it as this diagonal. So, right, so I can write here what we have learned, that covariance of x and y equals to the covariance of y and x, right? Hence the matrix is symmetric. Hence matrix is symmetric, right, about diagonal. Variance is symmetric. So n-dimensional, if it is an n-dimensional matrix, it would eventually lead to n by n matrix. So I just wanted to show you a little bit extended. That was a simpler one with a 2 by 2. With a 3 by 3 matrix, similarly in this way, it is the matrix is diagonal. Covariance between x and y and covariance between y and x has no value. Okay, in this next final part of the video, we are going to look forward for what it is called a covector. So now we will be talking only about covector. Now when I talk about covectors, generally covectors are known to be as row vectors. Now when I tell this, what I am trying to mean is that, for example, if I get a kind of a row vector 2, 4 and 1, right? This is a kind of a row vector, and then we get a column vector 2, 4 and 1, right? So this is the row vector, I can call it as R, and this is the column vector, which I call it an N. But it is actually not so. In this particular system is only applicable when we get a kind of an orthonormal basis, right? So we get a value something like E1 and E2, which we have used the conventions, right? X and Y. So vectors, this is true only in case of an orthonormal system where we get when things are perpendicular to each other. But row vectors and column vectors are not same. It has got different when the coordinate system is not orthonormal, right? So what we can tell is that row vectors are functions on column vectors. You can see on your screen, I have mentioned it, row vectors are function and column vectors. When I tell that, so what I mean to say is that there is a function which is coming in, it is going to take a kind of an input and it is going to get a kind of an output. So for example, if we take a kind of a row vector, say for example 2 minus 3, okay, and it is acting on a column vector, say for example 3 minus 4, right? So what we can do is that we can use this as a kind of a multiplication, and what we get from here is say for example 2 minus 2 2 minus 3 acting on 3 minus 4. So this would be, say for example 2 3, so it would be, say for example 2 multiplied 3 would be 6, and plus, if I take minus 3 multiplied by minus 4 will be 12, and we get the values at 18. So it's a kind of a function like which is acting and this row vector on a particular column vector, right? And it is showing the value. So this particular part, if I can use it as X, okay, let me use a different pen color. So it would be, say for example X, which is acting on say vector V, right? And it is eventually resulting to x1 v1 plus x2 v2 dot 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 dot, and it goes up till xn vn, right? So what I can do is that this can be neatly written with the usage of sigma. I can write this as sigma of I equals to 0 to n and xi vi, right? So this is a kind of a more compact notation. So what we can show in here is that we can write x takes in a value from the vector space V, and it produces a real integer which is r, right? So row vector takes an input. This row vector takes an input from the vector space V, and it gives back to the real number, that is which can be a scalar. Now for example, let us see, we get a case in which we are going to show how this inputs and outputs are related. What I'm going to show is that the addition and the scaling actually has got the associative and distributive property. So let us say that we take a row vector acting on two row vector which is acting on two column vectors, and we are going to add it. So let us quickly take a kind of an example. So we get so here we have got this one. I think this part is quite clear till now. So this is the row vector and this is the column vector. So we get in here, right? So we take a case when we have got values like 1 and 7, right? And it is acting on the values. So we are considering this to be an input, and we are taking values like 3 4, right? And we have got another one which had got values like 0 and 1, right? So the first thing what we can do is that the first part what we are going to do is that when these row vectors are adding, we can distribute the row vector, this part, into the inputs. This is the first way. So what we are doing, we are going to distribute the row vectors into two parts. So how it is going to look? It is going to look something like this. So we get the row vector 1 and 7, right? and we are going to distribute it between, say for example, 3 and 4, right? Plus again I take the row vector 1 7, and again I distribute between 0 and 1, 0 and 1, right? So what we are going to get this value, I will quickly calculate it for you. So it will be 3 plus 28, this will be 3 plus 28, and this will be plus 0 plus 7, so this will become 31 plus 7, and it will show as 38. So we get this value. So this is 1. We are splitting up the row vector between these two parts. So 1 and 7 here and 1 and 7 here. The second part, what we are going to find is that the same row vector, if we are adding the inputs together and then get the row vector and operating on the column vectors. Here we have distributed it, but what we are going to do over here is that we are going to take the same row vector 1 and 7, right? This is the second one. And what we are going to do, let me write it for you. 3 4 we have got the same thing, right? And 0 1 we have got the same thing, right? This is within brackets, this is a plus sign. So next step, what I'm going to do is that I'm going to take this row vector 1 and 7, and I'm going to distribute, I'm going to add these values together. So what we get is 3 and 0, yes, and 4 and 1, so I get 5. So I can put this one, and this will become in total 1 3 3 and 7 7 0 5, 3 plus 35, and this will be 38, right? So what you see over here is that this part, this one and this one, both of them are the same. Both of them are the same. So from here, what we can find is this. So from this particular part, what we are showing is that, say for example, if we are using the values of x, right, in this particular calculation, what we have done, right, and we take two vectors, say for example v plus y, right, so this can be written as x of v, which is a vector, plus x of y, right? As you can see, so both of these, if these are the same, so if you're taking the row vector and doing this and taking the row vectors, so this is 300 plus 1, this is the calculation. So we can write it as this. So one is that adding the inputs before and adding the inputs after. So I can call this as adding the inputs before, and this is what we call adding the inputs after, right? So we get the same result, isn't it? So this can be termed as something which you can say for example, a b plus c equals, right, equals to ab plus ac, and this is what we call the distributive property. So we will this is the distributive property. We will come to show, we will show you further that this, so this part is clear. So xv plus y equal to xv plus xy, which can be used by similar variables. Now for example, if we scale this vector, so this was done through addition. So let us see that if we can use the same variables and we can scale these vectors. So in order to scale the vector, what we can do is that, let us say we take the same values of 1 7, the row vector, and we use the values which is now changed a little bit. So what I can do, I can use -2, and I can use this as 1 4, right? So these are the values which we have got, right? So once we are scaling it, we can do the same way. We can distribute these values 1 7, the row vector, I can distribute here, right? And what I can do is that I can write this as -2 1, right, and -2 positive 4 plus 4, and I can close this one. So what I'm going to get is that 1 7 will remain here, and we will get the values as -2. Say for example I put this bracket, which is not a rigorous way anyway, so it will become what, -2, and this will -2, this will be -2 plus minus -56, which will be -58, right? So here we got the value of -58. So we got the same values, and let us use it in a different way where we do the addition together. So we get the values as -2, and then we get 1 4. We put these braces, and then we write as -2 1 7, and we write this as 1 4, right? So there is negative sign, only is -2. So what we get from here is that we can write -2. So what I'm going to do, what you can see this one here, -2, this has been carried here, right? And in here what I have done is that this -2, I will show it in a different pen so that it becomes clear. This -2 has gone over here, right? Right, and this -1 and -7 has gone over here. So this has carried over here. This is the way in which we are doing. So what we are going to get is that we get these values as -2, and again if I do the calculation, it will become -56, right? So this okay, let me show it for you. So this would be -2, and within the bracket I'm going to get 1 and 28. 7 was 28. So this would become -2 minus 56, and it would be -58. So again you see that the values stands to be the same, this part and this part, right? So even in the in case of scaling, we are getting the same value. So from here what we can do is that we can write say for example x, okay, I take a value, say for example m, and vector v, okay, equals to same like mx v, right? So in this case we can scale the input and we can scale the input or scale the output, and we get the same values, 58, -58 and -58. So this can also be written in ordinary variables. If I take a, b, c is also say for example equal to b, this one m is b and x is a, so ba c. So it again follows what is called the associative property. So from here now what we are going to finally what we have shown, let me show you the summary for this part. So here it comes. So let me explain to you. These are the 3 points which we have derived. So the first part shows a vector is a function so that it takes another vector and gives out an output which is in terms of real number, and it is a scalar. Point number 1. X v plus y w equal to x v plus x w, which is it adds the inputs and outputs and get the same result, so it follows the distributive property. Number 3 is that when we are multiplying, we are scaling these vectors, inputs or outputs, we are getting the same results. X mv is also equal to mx by v, so it follows the associative property. So just to show you that how we did that, this is the way in which we did. So you see this one becomes same using those variables, and this part, that would be for addition, this one also becomes the same in the previous, if you have shown in the calculations, this one equals. So that is why we have shown you, see this is the one. So you get 38 in both the case. So the first part shows that how we can summarize, the second part shows the addition, and this is the summary which shows the distributive and the associative property. Okay, so we have come to almost to the end of the video. When this part, now to mention, when this part and this part, both of them are working together, let me write it for you. This is what is called linearity. This is called what is called linearity. So let me show you what is the usual definition of linearity. Here comes the definition of linearity. So linearity means the property of a function of being compatible with addition, which we have seen, and scaling, also known as superposition principle. Now, if you ask me typically what is a superposition principle, let me just give you a this is just a name. So it is something like this. So a superposition principle states that, for example, if you get a kind of an input happening in this direction, and we call this input as A, right? And it is acting on a body. Say, for example, this body is X, right? And it shows some impulse. Then if there is another input, say for example the input is B, which is acting on another body which is Y, right? So we have to put it up at then. Let me show you in red, it becomes clear. So what is going to happen is that then A plus B, that is those two bodies, if I add it up, will be equal to X plus Y, right? If input A produces a response to the body X, input B produces a response to body Y, then A plus B will also respond to X plus Y. This is what is called the principle of, this is the superposition principle. Now, as we have called this as a linear function, so linearity is something which we are going to discuss again in the next part of the video. This is what is called a linearity. So obviously what you can understand from here is that if we are talking of linearity, then this part will also be the same. So if I take a variable, say for example f, and I take three variables f, x, y and z, right? And if I give it a value of 3x plus 4y plus 2z, right? So has similarities, so we can add them together. So if I can call f1, say x, y, z equals to 3x plus 4y plus 2z, right? And if I take another linear equation, f2 equals to xyz, it equals to 6x plus 5y plus 3z, just taking any values. So what we can do, we can use these values, so 9x plus 9y plus 5z. So we can add those things up. Also what we can do, we can apply the scalar multiplication. So if I write, say for example 2 multiplied by say for example this particular value, 3x plus 4y plus 2z equals to 6x plus 8y plus 4z. So what we have done is that we have used multiplication also. So anyway, it just wanted to show you that linearity means that it follows for those linear equations until we are raising to the power of 2, which will become a quadratic equation. So that brings to the end of the video. I think you have enjoyed it. So let me quickly show you a summary before we conclude. So what we have looked into is this. Part 1. We have seen what is a covariance matrix. We have actually plotted the values of covariance matrix. We have seen contravariant and covariant matrix in a kind of a visual representation, where the contravariant components are the parallel projections and the covariant components are the perpendicular projection. And we have seen how this value moves, and this particular part is moving in the opposite direction. The y moves from 0 to 3, and the x, this part moves from 3 to 0. We have also seen what is a covector. We have seen sufficient examples. We have also seen that how covector can be used as a function. And that is the reason that if it is a function, so it follows the principle of distributive and associative property, and covectors are linear functions. Now, one thing I would just like to mention before we end this video is that when you are talking of covector as a linear function, so next we would be talking about linearity, linear mapping and other things. Just remember that because covector or covariant vectors, which is related to covariant vectors, because they change from one to another in the same way, and that is why it is called a function. So we can take a value, we can increase it, say by 2 or 3 or 4, we can decrease it by -2, -3 or -4, and that is why it is used as a function, because a function behaves exactly in the similar way. So this brings up to the end of the video. I hope you have liked it. Please put up your comments. And you can like, and please do subscribe if you like the video. In the next part we would be speaking more about dual vector space, which is an important part, and then we will go towards linearity more in details before we complete the tensor series. Thank you for watching. Stay safe, stay happy, and have a nice day. Bye.